Now that we've looked at intermolecular forces and are able to identify them in very basic molecules, we need to be able to apply this to much larger molecules. And on the AP exam, that's generally what they end up giving you to evaluate so that they know that you know about your intermolecular forces. So let's look at some larger molecules. These are going to be very basic organic molecules. Here we have an aldehyde. So this is acetaldehyde. And we have, I want you to take a moment and think about what type of intermolecular force you would have. In this one, you are not going to have hydrogen bonding because this hydrogen is not directly attached to your carbon. This is going to be polar because this oxygen is quite electronegative and is going to be pulling on the electrons from all of these other atoms, leaving this entire molecule polar. So it would have dipole-dipole forces. If we look at this one, we recognize that we are going to have some polarity here because we've got our nitrogen and oxygen. Those tend to be very electronegative elements. And we see that we have a hydrogen directly bonded to a nitrogen. So here we are going to have hydrogen bonding. This hydrogen is going to be electron deficient and can seek out either these unshared pairs or these unshared pairs on a neighboring molecule. If you look at this one, this is a nice ether. And we are going to have some no hydrogen bonding because we don't have any electron deficient hydrogens here, but we do have this oxygen sitting here, so it is going to make this entire molecule polar. So it would undergo dipole-dipole forces. Here we have an ester. These are the things that give artificial smells or flavoring, or smells anyway, and we'll make some of those after the AP exam. So if you look at these, we've got this double bonded oxygen here and another oxygen here, but no directly bonded hydrogens, so no hydrogen bonding. But again, these tend to be very electronegative elements, so they are going to pull on those electrons, making this molecule polar. So we would have a polar molecule, meaning dipole-dipole forces. Here we have methanoic acid. This is also called formic acid. This is what fire ants kind of inject into your skin when they bite and makes it itch and burn. This is that COOH that we see on the end of acids, organic acids like acetic acid. And if we look at the type of bonding that we have here, we notice that we've got some oxygens, so definitely some polarity going on, but we do have a hydrogen directly bonded to this oxygen, and that is going to make this be able to undergo hydrogen bonding with other molecules. So we do have hydrogen bonding going on here, and so when you see that COOH, you are going to have hydrogen bonding. That can happen. This is methylamine, and when we look at these, I want you to notice this part right here, and I don't want you to get freaked out about looking at these molecules. An amine kind of acts like an ammonia, and when it's attached to these carbons, it's just like if it were attached to a hydrogen, and it's going to do what this molecule is going to do exactly what ammonia does, and try and collect a hydrogen in order to become ammonium, or collect another hydrogen here to collect that positive charge. And so you would treat it the same way as you would treat ammonia. Just a heads up. So if we just look at this for the type of intermolecular forces, so we have a nitrogen here, so we know we've got some polarity going on, and we have a hydrogen directly, actually two hydrogens directly bonded to this nitrogen. So we are going to have some hydrogen bonding going on in this molecule. Here we have ethane. So this is a very basic alkane, just carbons and hydrogens. Remember, this carbon-hydrogen bond is only slightly polar, and this molecule right here is very symmetrical. So if you get a compound that just has a bunch of C's and H's in it, those are alkanes, and they are non-polar, and it's worthwhile to go ahead and memorize that. So if that is a non-polar molecule, then we are only going to have London dispersion forces. But the more carbons and hydrogens you add, the more those will increase. Here I have an alcohol. We have an oxygen directly bonded to a hydrogen. This is methanol. This is going to be able to undergo hydrogen bonding because we have an electron deficient enough hydrogen that will seek out unshared pairs on neighboring methanol molecules. So any alcohols are going to end up being able to undergo hydrogen bonding. Okay, another thing that they're going to do on the AP exam is give you kind of answer choices and ask which one represents hydrogen bonding. So we just looked at an alcohol, and we know that it will undergo hydrogen bonding. The way this is drawn, these little equal signs right here represent a force of attraction. So is the diagram that I have right here representative of the hydrogen bonding that this molecule will undergo with other molecules of the same type? The answer is no. Yes, we have a hydrogen attracted to an unshared pair, but this hydrogen isn't electron deficient enough because it is not bonded directly to FO or N. So this attraction would not be hydrogen bonding. A better representation of the hydrogen bonding attraction would be this. So this hydrogen that's directly bonded to FO or N, in this case oxygen, is electron deficient and will be seeking out those unshared pairs. So this is hydrogen bonding. On your homework tonight, I have more practice on identifying what hydrogen bonding really looks like, because they do test that in many different ways, and you will have to be able to articulate it as well. All right, now I have some practice, and this will help with your homework. And the reason why we want to be able to identify our intermolecular forces is because they let us know about certain properties that these solutions will have, or substances will have. So the stronger the intermolecular forces between molecules, the higher the substance's melting and boiling points. That means the intermolecular forces are what has to be broken in order for a substance to go through a phase change. You have to break some of those attractive forces for a solid to go to a liquid, and then you have to break the rest of those attractive forces when that liquid becomes a vapor. That's what boiling points are, a measure of how strong the intermolecular forces are. So recognize that intermolecular forces are broken when we go through a phase change, not bonds. Bonds are much, much stronger than our intermolecular forces. And in this homework, I also included some substances that actually have bonds that would have to be broken. So you've got to be able to identify what type of attraction we're dealing with. So remember that atom-to-atom bonds are much stronger than intermolecular forces. These are only about 5% as strong as atom-to-atom bonds are. So in this first one, we're going to rank the melting points for each of these. So the first thing we want to do is we want to go through and identify what type of substance we have here and what type of intermolecular forces. So here we have a molecule, all nonmetals. This is an amine because I see that CH2 here. And that's going to have some hydrogen bonding in it. We have lithium chloride. This is an ionic compound, so this is definitely going to be the strongest attraction here. This is not intermolecular forces that are happening here, but ion-to-ion attractions. With this one, we've got a nitrogen in the middle, and it's bonded to 3 carbons. And I can draw something like that. Nope, it's not going to let me draw it. Let's go back. Okay, so we have a nitrogen that is directly bonded to 3 carbons.